The year is 1987, and a revolutionary idea is sweeping through the corridors of theoretical physics. Nobel laureate Steven Weinberg is at the center of this storm, ready to challenge the very fabric of our understanding of the cosmos. His weapon of choice: a simple yet profound question. Can the fundamental constants of nature vary across the universe? In this riveting episode, we delve into Weinberg's groundbreaking work and its profound implications for our perception of reality. We'll explore how his ideas opened up new vistas in cosmology and particle physics, forcing us to confront one of the most intriguing questions of our time. Does our universe exist in a grand multiverse? To fully appreciate the brilliance of Weinberg's thinking, we must first take a closer look at the cosmological constant, a concept that has puzzled scientists since Einstein first introduced it. The cosmological constant, represented by the Greek letter lambda, was initially conceived as a way to keep the universe static, a constant force countering gravity and preventing the universe from collapsing in on itself. However, as astronomical observations revealed an expanding universe, the purpose of the cosmological constant shifted. It became a tool to model this expansion, now known as dark energy. Enter the perplexing problem that has challenged generations of physicists. According to quantum field theory, the vacuum of space should be teeming with virtual particles popping in and out of existence. These virtual particles, though ephemeral, exert a significant energy, and it is this energy that constitutes the vacuum energy density. The issue arises when we attempt to calculate this value. The predicted value based on quantum field theory is astronomically high, more than 120 orders of magnitude greater than the observed value. This discrepancy has profound implications, suggesting that the universe as we know it should be vastly different from the one we inhabit. It implies that the universe would have expanded exponentially, preventing the formation of stars, galaxies, and ultimately, life itself. So how did Weinberg approach this seemingly intractable problem? His solution was both audacious and elegant. Instead of viewing the cosmological constant as a fixed universal constant, he proposed that it could vary from universe to universe. This radical idea opened up a new way of thinking, suggesting that our universe is just one among countless others, each with its unique set of physical laws and constants. But why would such a multiverse exist? Let us turn to the ancient Greeks, who believed that our physical world is composed of 4 elements: earth, air, fire, and water. These elements were thought to be the fundamental building blocks of reality. However, with the advent of modern science, we now know that these classical elements are not the basic constituents of matter. They are, in fact, composed of a far simpler set of particles: protons, neutrons, and electrons. Could it be that in some other universes, the fundamental particles of nature are different, giving rise to entirely new forms of matter and possibly life? What if our universe is just one of many where the elements are written in a different script? This line of thought leads us to an even deeper mystery: the origin of the fundamental particles themselves. Where did they come from, and what governs their properties? Weinberg's multiverse provides a tantalizing hint. Perhaps the properties of these particles are not fixed, but are instead determined by the particular universe in which they reside. In a universe slightly different from ours, the strong nuclear force might be slightly weaker, altering the stability of atomic nuclei and changing the periodic table of elements. This raises a fascinating question. Could there be other universes where elements more suitable for life, such as oxygen or carbon, are more abundant? Or perhaps there are universes where entirely new elements with exotic properties exist. But the implications of Weinberg's anthropic multiverse go even further. It touches upon the very essence of our existence. Are we truly unique in the cosmos, or are there other universes teeming with life? Did life arise only once in this vast multiverse, or is it a common occurrence? Weinberg's ideas, while controversial, have pushed the boundaries of scientific thought. They challenge us to consider the possibility that our universe is not an isolated island, but a part of a grand cosmic tapestry woven with countless threads of reality. While the multiverse remains a subject of debate and exploration, Weinberg's contribution is undeniable. He showed us that the constants of nature, once thought immutable, might hold secrets waiting to be uncovered. The stage is set for a new era in scientific inquiry. But the journey doesn't end here. There's more to the story, more to the fundamental fabric of our reality. As we continue to probe the depths of the cosmos, we find ourselves at the edge of a profound mystery. How do the fundamental particles of nature acquire their masses? This question, central to our understanding of particle physics, takes us to the heart of the Higgs mechanism. The Higgs mechanism is a cornerstone of the Standard Model, the theoretical framework that describes the behavior of fundamental particles. Central to this mechanism is the Higgs boson, a particle that was discovered at the Large Hadron Collider in 2012, confirming one of the last missing pieces of the Standard Model. But the story of the Higgs boson is not without its own set of puzzles. The mass of this particle, like the value of the cosmological constant, presents a problem. Theoretical predictions based on quantum field theory deviate dramatically from observations. Again, we encounter a discrepancy that threatens to tear apart the very fabric of our understanding. This conundrum highlights the limitations of our current theories. Quantum field theory, while incredibly successful at low energies, seems to break down at higher energies, hinting at the need for a more comprehensive theory of nature. Could the answer lie in the realm of the multiverse? Weinberg's ideas provide a compelling perspective. Perhaps the mass of the Higgs boson, like the cosmological constant, varies from universe to universe. Each universe with its unique set of physical laws and constants could have a slightly different Higgs boson, giving rise to different particle masses and consequently different forms of matter. This concept opens up a whole new set of questions. Are the variations in particle masses large enough to significantly alter the properties of matter? Could there be universes where elements and compounds behave in entirely new ways? Might there be universes where life, as we know it, is not possible due to the dramatic changes in chemical behavior? Weinberg's multiverse challenges us to reconsider the uniqueness of our universe. It suggests that the physical laws and constants that govern our reality might not be absolute, but relative to the particular universe. Our existence, once thought to be the result of a unique set of circumstances, might instead be a common occurrence in a vast cosmic landscape. Yet, despite the allure of these ideas, they are not without their critics. Some argue that the multiverse is not a scientific concept, because it cannot be tested or falsified. They claim that it is merely a mathematical construct that lacks observational support. However, others contend that the multiverse, while currently unobservable, might leave behind subtle clues in the cosmic microwave background radiation or in the patterns of large-scale structures in the universe. These potential observational hints are not only driving new research, but also fueling debates about the nature of scientific inquiry itself. Can a theory be considered scientific if it cannot be directly tested? Or does the potential for indirect evidence suffice? In the face of these criticisms, Weinberg's ideas stand firm. His work has not only advanced our understanding of cosmology and particle physics, but has also sparked a broader discussion about the limits and possibilities of human knowledge. Weinberg's legacy extends beyond his scientific contributions. He has inspired generations of scientists to push the boundaries of human understanding and to question the very nature of reality. His work has shown us that the universe never ceases to amaze, and that our quest to understand it is a journey without end. As we peer deeper into the cosmos, we uncover a reality more complex and awe-inspiring than we could have ever imagined. The multiverse, once a fringe idea, now takes center stage in our exploration of the universe. Whether or not it exists, the quest to understand it drives us to confront the deepest mysteries of existence. So let us continue to explore, to question, and to marvel at the wonders of the universe, for the journey, as always, is just beginning. So there you have it, a glimpse into the groundbreaking work of Steven Weinberg, and his vision of a multiverse where the laws of nature are not absolute, but vary from universe to universe. The quest to understand the fundamental structure of reality is far from over. There are many more mysteries waiting to be unraveled in the grand tapestry of the cosmos. But one thing is certain: thanks to the insights of brilliant minds like Steven Weinberg, we are equipped with the tools and the curiosity to keep exploring the endless wonders of the universe. So keep asking questions, keep seeking answers, and above all, keep marveling at the beauty and complexity of the world around us. After all, our journey through the multiverse is not just a scientific pursuit. It's a testament to the boundless curiosity and spirit of discovery that defines humanity. Until next time, keep looking up and let your imagination soar among the stars.